If you hold a mechanical watch close, you can hear its heartbeat, a steady, rapid tick-tock. But what's actually making that sound? It isn't the large balance wheel you see oscillating back and forth. That sound is the voice of a tiny, brilliant machine called the escapement. It's the critical link between the raw power of a wound spring and the serene march of the hands. Its job is to release that power one single gear tooth at a time. So let's follow that energy, because inside this sound is the 250-year-old secret to keeping perfect time. This brings us to the core problem every mechanical watch has to solve. At its heart is a tightly wound ribbon of steel, the mainspring. Like any spring, it wants to unleash all of its energy at once, in a single, uncontrolled rush. Worse, its pull is inconsistent. It pulls hardest when fully wound and grows weaker as it unwinds. You can't run a precision instrument on that kind of raw, chaotic power. The entire watch movement is a sophisticated system for taming that wild energy and rationing it out in perfectly identical, evenly spaced parcels. The mainspring is housed inside a circular, gear-toothed enclosure called the barrel. Modern mainsprings are made from advanced alloys like Nivaflex, which resist fatigue and magnetism, ensuring a long and consistent service life. A typical single barrel can power a watch for about 2 days. Some designs use 2 barrels in series. 2 stretch that power reserve past 3 days. But the challenge of the spring's uneven pull remains. Watchmakers have clever solutions. Automatic watches use a slipping bridle on the spring's outer end, which lets it slide against the barrel wall once fully wound to prevent damage. Many manual wind watches use a Geneva stopwork, a small Maltese cross-shaped part that physically blocks the barrel from being wound too tight or unwinding too far, keeping it in the most stable, linear portion of its torque curve. From the slow, powerful rotation of the barrel, the energy flows into the gear train. This series of interlocking wheels and smaller pinions is engineered to do one thing: trade raw force for rotational speed. As power moves from a large wheel to a small pinion, the speed increases and the torque decreases. 2 of these wheels also perform a visible job. The center wheel, true to its name, is usually in the middle and rotates once per hour, driving the minute hand. Further down the line, the 4th wheel makes one full rotation every 60 seconds, providing the motion for the seconds hand. Under the dial, these calm, steady hands hide a cascade of precisely calculated gear ratios. At the very end of this cascade is the escape wheel. It's small with distinctively shaped teeth, and compared to the rest of the train, it's sprinting. In a common modern watch, beating at 28,800 vibrations per hour, this wheel is spinning at about 32 revolutions per minute. All day long, the mainspring barrel creeps along, while just a few millimeters away, the escape wheel races. This high speed is what enables the escapement to chop time into the fine, controllable increments needed for accuracy. This brings us to the star of the show, the Swiss lever escapement. First invented by English watchmaker Thomas Mudge around 1755 and perfected over the next 2 centuries, its geometry is a masterclass in controlled friction. It consists of 2 main parts: the escape wheel we just met, and a pallet fork, which holds 2 small ruby jewels called pallets. As the balance wheel swings, it moves the pallet fork, causing these 2 pallets to alternately lock and release the escape wheel, one tooth at a time. During each release, a tooth slides along the angled face of the pallet, giving the fork a tiny push. This push is transferred to the balance wheel via an impulse jewel, keeping it swinging. The cycle is precise. A tooth locks on the entry pallet's locking face. The balance swings, unlocking it. The tooth then impulses the pallet's impulse face. The wheel advances, and the next tooth is caught by the exit pallet. The process repeats in reverse. So that tick-tock sound is actually 2 distinct events. The tick is the sound of an escape wheel tooth impacting the locking face of one pallet stone. The tock is the sound of another tooth hitting the other pallet stone after the balance swings back. On a watchmaker's timing machine, you can see these 2 sounds as 2 separate lines of dots. If the time between tick and tock is different from the time between tock and tick, the watch has a beat error. A well-adjusted movement has a beat error near 0, meaning the balance wheel's oscillation is perfectly centered. This whole process relies on sliding friction, which must be managed by incredibly precise lubrication. A watchmaker applies a droplet of oil so minuscule you can barely see it. Too much oil creates drag, too little allows wear. It's a microscopic balancing act. The escapement's job is to sustain the motion of the timekeeper itself, the oscillator. This consists of the balance wheel and the hairspring, a delicate spiraled spring at its center. Together, they form a harmonic oscillator, like a child on a swing with a natural, consistent period of oscillation. The escapement's role is to give a gentle, precisely timed push on each swing to counteract friction and keep it going. The key is to deliver this impulse without disturbing the oscillator's natural rhythm. The health of the system can be judged by its amplitude, the angle the balance wheel rotates through on each swing. A healthy, fully wound watch will show an amplitude between about 270 and 310 degrees. A significant drop can signal a problem, like low power or excess friction. To make the oscillator's rhythm as stable as possible, watchmakers focus on the hairspring. A key innovation from Abraham Louis Breguet in 1795 was the overcoil, where the spring's outer turn is raised and curved back toward the center. This helps the spring breathe more concentrically, making its rate more consistent regardless of amplitude, a property called isochronism. Modern hairsprings use advanced alloys or even monocrystalline silicon to be virtually immune to temperature changes and magnetism. The frequency of the oscillator also matters. Many modern watches beat 8 times per second. Higher frequencies, like the 10 beats per second of Zenith's famous El Primero movement, can improve stability by averaging out errors more quickly. But this isn't a free lunch. Higher beats consume more energy and increase wear, requiring more robust engineering and lubrication throughout. To combat the wear from all this constant motion, watches use jewels. A standard time-only mechanical watch often has 17 of them. These aren't for decoration. They are functional bearings made of hard, low-friction synthetic ruby. They are placed at the pivot points of the fastest-moving gears, on the pallet fork, and as the impulse jewel on the balance. Steel pivoting on ruby is far more durable than steel on brass. Even with these jewels, the Swiss lever escapement is intentionally inefficient. Only about a third of the mainspring's energy actually reaches the balance wheel. The rest is purposefully consumed by the sliding friction of the escapement's locking and unlocking action. It sounds wasteful, but this is the price of control. The watch deliberately trades raw power for unwavering metronomic precision. For nearly 2 centuries, the Swiss lever reigned supreme. But in 1980, the English master watchmaker George Daniels patented the Co Axial escapement, famously adopted by Omega in 1999. Its complex multi-level design separates the locking and impulse functions. The key benefit is that the impulse is delivered with a tangential rolling action, rather than the long sliding action of the Swiss lever. This dramatically reduces friction and the stress on lubrication at the most critical point, theoretically extending service intervals. It's a brilliant reimagining of the problem, and the first truly new, mass-produced escapement in modern history. So what does all this engineering achieve? A high-quality mechanical watch, certified as a chronometer by the Swiss Official Chronometer Testing Institute, or COSC, must maintain an average daily rate of between -4 and +6 seconds per day across a battery of tests in different positions and temperatures. That's better than 99.99% accuracy, and it achieves this while withstanding the motion of your daily life. It's a system where the barrel turns once or twice a day, the seconds hand turns 1440 times a day, and the escape wheel turns over 46,000 times a day. And the balance? At 8 beats per second, it completes over 252 million oscillations per year. All these moving parts, working in concert to translate a simple unwinding spring into a near-perfect measure of time. Now, listen to that sound again. Each tick is a high-speed collision, a transfer of energy, and a moment of perfect lockstep control. It's the sound of one gear tooth being released and another being caught, of the balance wheel receiving the tiny push it needs to complete another journey of exactly 1/8 of a second. It's a ritual of controlled impacts, repeated hundreds of millions of times a year. This is the beauty of the mechanism. The lever escapement is a 250-year-old idea, polished with modern materials but fundamentally unchanged. It's a testament to an ingenious solution that turns chaos into order, one tooth at a time. If you enjoy seeing the inner machinery of the things we use every day, you'll feel right at home here. Subscribe and let us know if you found this useful. We have more deep dives into engines, microchips, and the hidden systems that run our world. Thanks for watching, and we'll see you in the next one.